The next speaker is Ranjan Laha.
So, good morning everybody. First of all, I would like to thank the organizers for inviting me to this wonderful conference, the local organizers for the awesome hospitality, to the participants with whom I am having some great discussions, and all the people present here for this talk. So, I will be talking about a topic which includes GR, cosmology, relativistic astrophysics, and gravitation, particle physics, and various different things. The topic is dark matter. All right. More precisely, the topic is how to detect dark matter. All right. So, I will be talking about a technique that I am working on, basically how to detect dark matter using the observations of the sun, and this is something that I am working with currently with Taroknath Maiti, who is a postdoc at IISc, Akash Kumar Shah, who is a PhD student at IISc, is also present here, and Shagnik Mondal, who is an undergraduate student at IISc. Okay, so let us proceed. So, the theme of the conference is tensions in standard cosmology. All right. Whenever you have tensions, the way I look at it, that implies opportunities in standard cosmology. Right. Whenever there is a tension, there is an opportunity to do something new, which people have not done, and this is the strategy that I will take. So, what is the tension? The tension that I will be trying to address is what is dark matter. More precisely, what are the non-gravitational signatures of dark matter. All right. This is a question that has been plaguing us for the last 40 years, and we still do not know the answer. And what I will try to convince you is trying to use information from astrophysics, particle physics, cosmology, GR can lead us to answering this great question. And the opportunity here is basically, since the existing probes have not yet worked, we can try to think of new probes of detecting non-gravitational couplings of dark matter, right? And I will try to explain how that works. Okay, so this is sort of the prelude to my talk. Slides are not changing. Okay, yes. Okay, so these are the contents. So I will first introduce dark matter, give a brief introduction to dark matter. Then I will be talking about one way to detect dark matter, that is called indirect detection. I will tell you how it works. Then I will be talking about how to detect dark matter in a process called direct detection. I will again tell you how it works. And then finally I will come to our work, where I will show you that you can probe dark matter electron scattering by looking at the sun using high energy neutrinos. And I will conclude. All of these topics, basically first three topics, can be talks by itself. In fact, can be workshops or conferences by itself. So I won't be able to cover everything. So if I miss any of your favorite topics, feel free to complain, and I'll be happy to talk more about it. Okay, good. So the gravitational detection of dark matter. This is a busy slide, and I've made it intentionally busy, just to show that if you do any astrophysical observations, astrophysical or cosmological observations at scales beyond a kiloparsec or beyond, you require dark matter, right? And this is not even listing all the signatures or gravitational detections of dark matter that we have made. So let's start from here. So this is the rotation curve of this galaxy NGC 6503. What is plotted is, on the x-axis is the distance from the center of that galaxy. On the y-axis is the velocity of stars and gas. All right. These are the data points. All right. And if these data points you can see, right, these are the data points. And if you assume that the galaxy only has baryonic matter, that means standard model matter, it would have followed something like this, the disk and the gas, something like this. You require something extra, the dark matter halo, to explain the observations. This is the proof that dark matter exists at scales of 10 kiloparsecs. All right. Next is this picture. This is a picture, this is an artistic rendition of the Milky Way. If you go outside the Milky Way, take a snapshot, this is how it will look like. This is the galactic center, this is the galactic bulge, this is the galactic disk, these are the large imaginary clouds, and some of these are dwarf galaxies. The motion of the dwarf galaxies can only be explained by assuming that the dwarf galaxies themselves are embedded in dark matter halos, and the Milky Way itself is embedded in a dark matter halo. All right. This is the proof of dark matter at scales of hundreds or 200, 300 kiloparsec. Let us go to a larger distance scale. This is the prototype, this is the first example of galaxy cluster collisions, all right. Galaxy clusters are thousands of galaxies bound together. So this is called the bullet cluster, where two clusters collided. What you see in this pink or red, whatever, is the signature of gas. This is basically detected by Chandra. This is where relativistic astrophysics comes in, and in blue is basically the mass of this cluster that was seen by lensing, by using GR observations, lensing observations, right? And you can prove that this tells you the existence of dark matter at megaparsec scales. Note that this is not the only cluster we know of. We know of at least 70 or 80 more clusters. Sorry, 70. This is not the only merging cluster that we know of. We know of at least 70 to 80 more merging clusters. In all of them, we have a signature of dark matter. So these are the signatures of gravitational detection of dark matter at scales of megaparsec and beyond, so something like of the order of megaparsec. This is the pie chart of the universe, the energy density of the universe from the CMB, from the Planck measurements, and you can see that 27% of the energy density of the universe comes from dark matter. All right. Note that this number is known extremely well. The uncertainty on this number is 1.2%. All right. This is the proof that dark matter exists at gigaparsec length scales. Right. And finally, if you are a theorist, you can run a simulation in your laptop. The gadget code can be run on a laptop, and you can show that in order to match the observations, you require you require dark matter. All right. So this is something which you cannot run on a laptop from the illustrious collaboration. The left hand side is the real observation. The right hand side is the mock observation, and this looks identical. I mean, you just don't do it by seeing. By the way, you do various statistical measurements, and you can show that this actually matches extremely well. So this is a theoretical proof that dark matter exists. All right. So given the fact that we have been making these observations for, if you include Zwicky's observations, it's almost 90 years. What do we know of dark matter? We actually know a lot about dark matter, all right, and also we do not know a lot about dark matter. So what do we know? So first thing that we know is that dark matter must be non-relativistic. Currently, dark matter must be non-relativistic, all right. That is something that we know. So any candidate that has to be dark matter must be non-relativistic now. Second, dark matter must have weak interactions with standard model particles, all right. So here I put weak in quotation marks. What does that mean? That means it need not be the strong weak, that weak force. It just has to be weak in an English way. It can also be the weak force that we know of, but this is here weak is also used as an English weak, right? It's weak. And then we know that the lifetime of whatever is the dark matter candidate must be larger than the age of the universe. Why? We see dark matter around us. The smallest length scale in which we see dark matter is roughly a kiloparsec. So if you make observations around the sun at a distance of kiloparsecs, you will find dark matter. So that tells you that whatever is the dark matter candidate, it must exist now. So these are profound things that we know of. But we also do not know of many different things. First, what is the mass of the dark matter candidate? All right, dark matter must be something, right? I mean, everything around us is made up of electrons, protons. So what is the dark matter made up of? And if it is made up of something, what is the mass of that? We do not know that. We do not know what is the lifetime of the dark matter candidate. I told you it must exist now, but what is that number? That when I say it must exist now, that tells you the lifetime is greater than some number. But what is that? That's an inequality. What is the equality? Is there an equality? What is the lifetime of the dark matter candidate? We do not know that answer. And finally, we also do not know what is the interaction strength of dark matter candidate with itself and also with standard model particles. All right, things which we do not know, and we want to know all of these. Okay, so there are plethora of dark matter candidates. There are lots of dark matter candidates. All right, I mean many things can be made into dark matter. Right. The lowest mass a dark matter candidate can have is roughly 10 power minus 22 eV. All right, and I can explain. I don't have time now to explain, but if you're interested, just talk to me. I'll be happy to explain why is this. The highest mass a dark matter candidate can be, and yet constitute a large fraction of the dark matter, is something like 100 solar mass. All right, so these are like black holes, primordial black holes. All right, so remember this is a wide range. This is I think 90 orders of magnitude, right? And the important thing is we do not know where it can lie. It can lie anywhere in between. It can be this, or it can be somewhere in between. And it's important to test all well motivated candidates. given that we do not know that. It's also important, as I said, to test all regions of the dark matter parameter space and all different couplings. We do not know how dark matter couples with standard particles. Given that we do not know that, it's important to use as much experiments as possible, as much theory as we know, to test all different dark matter couplings, all different couplings of dark matter and standard model particles. Okay, good. Okay, so this is a nice figure taken from the Quantum magazine. It sort of explains this thing. I mean, the lightest mass is 10 power minus 22, 23 eV. Heaviest mass is few tens of solar masses. There are lots of talks on this in this conference on various different parts of it. For example, if you do primordial black holes, that's where you require a bit of GR, you require particle physics, astrophysics, cosmology to understand it. There was talk by Akash Kumar Shah and Priyank today. Dark matter can be a very heavy particle, few PeV or more, and you can use various relativistic astrophysical observations to constrain that. There's a talk by Vishek Dubey, and there are many other talks which I'm not mentioning, but I'm happy to talk more. Okay, so how do you detect dark matter? Right? How do you detect particle dark matter? In this talk, I'll be talking about particle dark matter. So this is a cartoon Feynman diagram, and if you don't understand it, let me explain how do you read it. So here SM stands for standard model, DM stands for dark matter. Okay. When I draw these two lines, these are asymptotic initial states or final states. All right, depending on which way I look at the figure. So these are either in the initial state or in the final state. Okay. So let's look at the figure from in this direction, from left to right. So the initial state are two standard model particles, the final state are two dark matter particles. What does that mean? So that means you are colliding two standard model particles to produce two dark matter particles. And this is the search strategy that one uses in colliders, all right, to produce dark matter. Let's look bottom up. What does it show? So in the initial state, we have a standard model particle and also a dark matter particle. In the final state, there is a standard model particle and a dark matter particle. This is the way of direct detection. You put some target in hopefully background free environment. You hope at some point the dark matter particle will come, do something to the target, break it up, do something, and you detect that breaking up signature. Right? That's direct detection. There are, again, these are many experiments listed. There are many more experiments. I mean, there's lots of experiments. I'll mention some of them later. Finally, you can also see this diagram, read this diagram from right to left here. So what does this mean? So in the initial state, there are two dark matter particles, and they produce two standard model particles in the final state. Right? That means dark matter particles annihilate to produce standard model particles. This is called indirect detection, and this is again a strategy used by almost all, in fact, all astrophysical observatories or telescopes to search for dark matter. Right? And these are names of some of them. Right? Okay, good. In the middle, there is a blob. This is where particle physics comes in. Right? I mean, how do you connect dark matter with standard model particle? Right? All right. And that's also a sort of like the theory way to understand this thing. Okay, so let's talk about dark matter indirect detection. So what is dark matter indirect detection? So here, what we do is we look at a distant part of the galaxy or the universe. We make cosmological observations to search for dark matter. So let's look at this object. This is, say, some cosmological or astrophysical source. We assume that inside that object, dark matter particles will annihilate to produce standard model particles. So again, you look at the figure from left to right, two dark matter particles in the initial state, two standard model particles in the final state. It will annihilate to produce standard model particles, and we are on Earth, we are trying to detect these standard model particles. All right. Technically, we search for dark matter annihilation or decay products from astrophysical or cosmological observations. The process that we are looking at is DM goes to SM. Dark matter goes to standard model particles. Okay. Good. So what do we search for? We search for an excess of standard model particles over the expected astrophysical background. We search for all standard model particles that can exist. We search for gamma rays, we search, photons, not just gamma rays. We search for all kinds of photons, neutrinos, antineutrinos, positrons, antiprotons, everything. Everything that we can observe, we try to search for this. And the cartoon way to understand this is as follows. What is plotted in this cartoon is energy on the x-axis, energy of the messenger of the messenger in the x-axis. So that means energy of these things, any of these things, and the flux on the y-axis. Typically, astrophysical processes give you a power law. All right, so this is the expected astrophysical background. Typical astrophysical processes give you a power law. If dark matter annihilation happens, it will typically give you a bump like this on this power law. If you see this, you say, aha, this is my dark matter candidate. I have discovered dark matter. All right. Turns out the thing is not that easy. It's not like drawing a cartoon. It takes time. So obviously, as I said, spectral features are useful. That means this spectrum, the fact that there is a cutoff at the dark matter mass, that is useful. This is because dark matter is non-relativistic. Again, I can explain more if you're interested. And what do we look at? We look at everything. We look at everything in the sky which we can look at. We start from the sun, the Milky Way galactic center, Milky Way halo, dwarf galaxy, galaxy clusters, cosmic micro background, everything, absolutely everything, to search for dark matter. This is an important problem, and it's useful to search everywhere to answer it. So what are the indirect detection targets? So the various targets are listed in this figure. So if you look at the galaxy, our galaxy, this is the galactic center, this bright spot, and this thing. So we look at the galactic center. The galactic center is extremely close to us. This is the closest region of the sky where there is lots and lots and lots of dark matter. So this is the brightest dark matter source in the sky, no question about it. But this is where almost all astrophysics is there. So the backgrounds are extremely high, right? So signal is very high, background is very high. Signal to noise ratio, well, we have to decide what happens. We can dwarf spheroidal galaxies. So these are satellite galaxies around the Milky Way. All right, these do not produce astrophysical gamma rays. I mean, there's a caveat. There's a recent paper on it. I can discuss more later. So that means there the background is really low, but they have a large mass to light ratio. All right, so they can give a signal of dark matter. Dark matter clumps. So these are small. These are smaller than dwarf galaxies. So these are small objects which do not host galaxies, all right, or even dwarf galaxies. I mean, can they be bright enough? We do not know. Can they increase the signal? Probably. We do not know. And finally, we can look at the whole halo, the whole dark matter halo of the Milky Way, right? And we can try to find again. There are pros and cons. We can also look at the extragalactic signal. That is, look at the whole cosmology and try to find out dark matter. Again, there are pros and cons. This is sensitive to how dark matter halos evolve, but however, there are challenges in trying to predict how things work, right? Obviously, you can look at galaxy clusters. Again, there are pros and cons. Maybe there is huge amount of dark matter signal boost. This is what it means, but the backgrounds can also be very high. Bottom line, we should look at everything to search for dark matter, all right? Currently, dwarf spheroidals and the galactic center give the strongest constraints, but it's possible that we will find a signal somewhere else, right? So it's useful to look at everything. So this is a map of the parameter space of dark matter, indirect detection searches using neutrinos. So what is this? So what is plotted on the x-axis is the dark matter particle mass in GeV, right? Note that the scale is going from 10 power minus 2 EV, sorry, 10 power minus 2 GeV to 10 power plus 7 GeV. In fact, it can even go further, all right? It is not plotted. On the y-axis is sigma v. What is sigma v? This is the thermally averaged annihilation cross-section times relative velocity. That means this sigma is the annihilation cross-section of two dark matter particles producing neutrinos. This process, this is something we do not know, multiplied by the relative velocity, and then we do a thermal average. So that's sigma v. Again, note the scale. Anything that you see shaded, that means is ruled out. All right. So what does it mean? This means if the dark matter particle mass has a mass of 10 GeV, all right, and if it has say a sigma v of 10 power minus 20 centimeter cube per second, this is in the shaded out region, ruled out. It cannot be. If dark matter particles goes to neutrino and antineutrino, these are all flavors, by the way. So these are constraints from various different experiments using various different search strategies that they have, starting from Borexino, Kamland, Super Kamiokande, Ice Cube, and then there's also Ice Cube. So even their higher masses using PROJ and other telescopes, you can also find these limits, right? These dashed lines that you see are basically projections. What will future telescopes do? All right. So you can see there are lots of the projections covering the whole range, even higher. This line that you see, this dotted line, is sort of like is also called the thermal relic abundance. This is sort of like a theoretical lamppost. All right. It is useful to a certain extent, but it's not the end all and be all. So this line tells you if dark matter is produced cosmologically in thermal processes, what should be the sigma v versus mass? This is this line. All right. This is the unitarity limit. This is basically, it comes from some quantum field theory considerations. All right. Basically saying that if dark matter is thermal and if dark matter is a point particle, it cannot have a mass greater than this range. It cannot have a mass here. All right. But note that this is a theory. I mean, nobody tells you that dark matter has to be a point particle. It can be a bound state. Then this line is not valid. All right. So you can do the same thing, same plot for gamma rays and antiprotons. All right. So this is the latest plot from this Dimaudo et al. This just came out last week. What is plotted on the x-axis is the dark matter particle mass. So here there is a shorter range plotted, but we can also go to higher ranges and smaller ranges. Higher masses and smaller masses. It's just not shown here. If you are interested, please come and talk to me. I'll be happy to chat. What is plotted on the x-axis is again, on the y-axis again the sigma v. Again, anything, all of these lines that you see, anything above is ruled out here. All right. So this line that you see, and here you are assuming that dark matter analyzed to BB bar. All right. Dark matter is analyzing to BB bar, bottom and anti-bottom quark. What does it do? So here's where particle physics comes in. The bottom quarks hadronize, produce hadrons, they decay, produce gamma rays, and that's the gamma rays that we are looking at. All right. It also produces antiprotons. Right. Anyways, so the gamma ray limit. So this is if you use the classical dwarfs and the ultra faint dwarfs. So this is the limit that you get. Anything above is ruled out. Right. If you just use the classical dwarf, you get this limit. Right. So you can see there's some improvement by using the ultra faint dwarf galaxies. These are the other limits from other papers, Alvarez et al., Abdullah et al. Okay. This line is the limit from antiprotons. Again, BB bar will hadronize, decay, produce antiprotons, and we have measured antiprotons very precisely. Given the fact that we have not found an excess of antiprotons over expected backgrounds, this is the line. So anything above is ruled out. This is the thermal line I told you. It's sort of like a theoretical lamppost that you try to hit, and these are basically, they are hints of that we have detected dark matter probably from the galactic center. Probably not correct, those hints, but if they are true, this is where dark matter must be. All right. I mean, they are heavier mass. I mean, as I said, dark matter can be much heavier. In fact, using the recent observations of Tibet A's gamma experiment, that's a high energy gamma ray experiment, which has actually which has made a great discovery about galactic high energy gamma rays. You can constrain dark matter. This is in this paper that we worked on, and there's also a recent paper by the Laha collaboration. That's again a gamma ray observatory, which has observed gamma rays, and they have also produced some of the leading limits on dark matter interactions. Okay. Good. So that was a 10-minute introduction to dark matter indirect detection. Dark matter direct detection. Dark matter direct detection can be done in various ways. All right. Here I'll be talking about dark matter electron scattering. You can also do dark matter proton scattering. Right. If you're interested, okay, come and talk to me. I'll be happy to chat. So what you do here is as follows. You take a target. I'll tell you what kind of targets you take. You take a target, keep it in an underground lab to shield it from backgrounds. Use various sophisticated techniques to eliminate the background, and you hope that at some point a dark matter particle will come, kick out the electron, and you see the signature of that electron getting kicked out. All right, and there are various signatures you can search for. All right, so this is dark matter electron scattering in a cartoon picture. So this is obviously sensitive to dark matter electron coupling. All right, and this measuring this electron recoil, you can use different techniques to measure this electron recoil depending on which target you use. All right. So this is generally sensitive to smaller dark matter masses than what can be measured by using dark matter proton scattering. I mean, dark matter can also come and scatter with this nucleus. All right, that is not what I'm talking about here. All right, but typically dark matter electron scattering is sensitive to lower dark matter masses than dark matter proton scattering. Right, this is just a choice. I'm assuming dark matter only couples to electrons, not with protons. All right. This is just a kinematic effect. You can just show that this is just kinematics. All right. And there are many ongoing and near future laboratory experiments trying to search this dark matter electron scattering. Right. There's Sensei, there's Xenon. I'll tell what are these experiments. All right. There's Xenon, various versions. There's Dark Side 50, CDMS, Edelweiss, Dumick. And there's been tremendous progress during the last few years. Last 10 years, this field has absolutely exploded, like beyond anybody's imagination. So this is the latest plot, the most updated constraint on dark matter electron scattering. All right. So what is plotted on the x-axis is the dark matter particle mass in MeV. On the y-axis is the dark matter electron scattering in centimeter squared. Right? Anything that is shaded is ruled out. So let's look at this line, the Sensei line, Sensei 2020 line. So here the target is silicon, right? Silicon has the smallest target mass. Again, due to various considerations, they have the smallest target mass. However, they have the lowest dark matter threshold. You see, they can constrain dark matter at masses of 10 MeV, which nothing else can constrain, right? And this is most sensitive to dark matter masses at 10 MeV. So this is where this curve has the minimum around 10 MeV. Okay. Next is argon. So this is this line, this dark side 50 2022 and this dark side 50 2018 line, right? So this has a mid-range target mass and it has a mid-range dark matter mass threshold. Right? Note that this constraints weaken at at greater than 10 MeV, right? This dark side 50 constraints weaken at say 20 30 MeV. That's what I mean by mid-range dark matter mass threshold. It's not as sensitive as silicon. It's most sensitive to dark matter mass of 50 MeV. So if you look at this plot, the lowest is 50 MeV. And finally, the xenon. This has the largest target mass. I'll tell you what some of these numbers are later in the next slide. However, this has the heaviest dark matter threshold, right? So this is xenon 1T 2019, Panda X 2021, and xenon 10 2017. Right? This one you can sort of neglect. There's some problems, but anyways, just concentrate on xenon 1T and the Panda X 1T 2021 and 2019. They have the largest target masses, but they have the heaviest dark matter threshold. So you see these limits start dying at 50, 60 MeV. This xenon 1 ton limit starts dying it, right? And they are most sensitive to dark matter masses of 200 MeV, somewhere here, most sensitive. This is where the minimum is. Right. Note that this plot assumes the standard halo model of dark matter. The dark matter velocity distribution is Maxwell-Boltzmann. That need not be the case. That's something that we worked on recently. What is the effects of dark matter? What are the effects on this plot if the dark matter velocity distribution is not Maxwell-Boltzmann? There are substructures, and there's also other papers by Tarok, Shambu, and others where they have also looked into similar things. Okay, so if you look at this plot, it's one thing that should come in your mind is that this plot ends at 1000 MeV, 1 GeV. What about higher masses? I mean, is dark matter not there? Dark matter can be there at higher masses. Dark matter can interact with electrons at higher masses. How do you detect it? Right? So that's the thing. How to probe heavier dark matter masses? These limits actually do not stop here. Right? These limits will continue at higher masses with 1 over m chi scaling. And I can explain again. I don't have time here, but I can explain later why is it 1 over m chi scale. You just take this limit, just scale up. It just keeps on going. There's no stopping this limit effectively. Up to a certain point. But that's something for some other talk. I can explain. So the question is, remember, these limits are continuing, right? All of these limits are continuing. So you can ask, wait, good. So that means there is a way to probe heavy dark matter. Basically, these limits, you just make this plot at higher masses. That's the easy way to do it. But then you can ask, wait a minute, is there a way to improve our sensitivity, right? So this just goes as 1 over m chi, keeps on going. But can we do better? The answer is obvious, right? The answer is increase the exposure. What does that mean? Build a bigger detector and run it for a longer time. It's sort of obvious, right? You make bigger detectors, run it for longer times, you will get more, your experiment will be more sensitive. So what are the numbers we are looking at? So dark side 50, which is this thing, has an exposure. So exposure here, basically the target mass times the lifetime, how long the experiment has done, is 12,000 kilogram days, roughly. Sensei has 20 gram days, and xenon 1 ton has 22 ton days. These are huge, huge exposures. Can we do even better? That's again I'm asking. And here I must credit my postdoc Tarok, who actually found out this answer. The answer is yes. There is a dark matter detector which has huge amounts of exposure. That is the sun. The sun, as a dark matter detector, has orders of magnitude larger exposure. I'll tell you in this slide how much. It has been moving through the dark matter halo through its entire life. That means if dark matter interacts with the sun will have a signature in it. Right? So what is the total exposure? If you take the sun's mass times the lifetime, it's 4.6 solar mass gigayear. orders and orders and orders of magnitude larger than what we can have in the lab. So the largest number we have is 22 ton days. This is 4.6 solar mass gigayears. Huge. All right. So the question is, can you use the sun as a dark matter detector? The answer is yes. That is something I'll talk about here. Do dark matter particles interact with the sun? I'll again explain here. And can we detect the signature of dark matter inside the sun? That also I'll explain. Okay, good. So do dark matter particles interact with the sun? So this is a cartoon way to show how dark matter particles can interact with the sun. Assume that there is a dark matter particle at infinity with a velocity u chi. I mean, here infinity means just far away, all right, far away from the gravitational effect of the sun. It gets gravitationally attracted towards the sun. When it reaches the sun's surface, it has a velocity of u chi square plus v escape square root. V escape is the velocity, escape velocity of the sun. This is a standard physics problem that we do. Extremely standard. This is actually, you can use school level education to search for dark matter. This is the example, right? So u chi, and it comes here. Now is where the fun comes in. Typically, dark matter does not interact with anything else. So it will just come in, it will just go out again, school level physics. But turns out, if dark matter has a scattering with electron with some cross section, sigma e, this is the only new physics that I will be talking about. It can scatter with the electron. So there is a two body scattering, dark matter, solar electron goes to dark matter, solar electron, two body scattering. There is a probability that the final velocity of the dark matter after scattering is less than the escape velocity of the sun. So probably you can just do that. And then what will happen? Well, the dark matter will get captured. That's it. All right. So this is what I have basically said. Note that there is only a small fraction of dark matter particles which will scatter with the solar electrons. All right. There are lots and lots of dark matter particles going through the sun. Only a small fraction will get scattered, and then even a smaller fraction will get captured inside the sun. This thing, even a smaller fraction will do. All right. But again, I mean, these are things which you can quantify and which we have quantified. This is an equation. You don't have to go through the details of the equation, but they just calculates the capture rate. So what does the capture rate depend on? So obviously it depends on the total number of electrons inside the sun. This is what it is. Number density of electrons times the volume. You integrate. That's the total number of electrons inside the sun. This is the incident dark matter flux. How much dark matter particles are hitting the sun? It depends on the number density of dark matter particles. So this is the local energy density of dark matter particles divided by the mass. That's the number density. This is the dark matter velocity distribution, and this is basically this factor. As I said, it gets gravitationally attracted towards the sun. This is the capture probability. This tells you, given a dark matter interacting with the solar electrons, what is the fraction? It will get captured inside the sun by having its final velocity less than the escape velocity. And this is the scattering cross section. Right? Note that we are not the first persons to think about these things. Right? There have been other people who have already thought about these things. At least these 4 papers I know of. All right. So how much dark matter is captured inside the sun? Obviously, it depends on the dark matter particle mass, and it depends on the sigma e. These are the main dependencies. You can show that if I assume that dark matter particle mass is 100 GeV, all right, a proton mass is 1 GeV. So if the dark matter is 100 times heavier than the proton, and if it has a cross section of 10 power minus 39 centimeters squared, then the amount of dark matter captured inside the sun is something like 10 power minus 17 solar mass. What does that number mean? These are actually masses similar to masses of asteroids. Some asteroids have this mass. Right? So that means, so this is a range of dark matter particle mass and cross section which is not yet ruled out. So even considering parameter space which are not yet probed, there can be an asteroid's amount of dark matter inside the sun. What does that mean? I mean that has to have a consequence. This is what we will talk about. Okay, good. So let's come back to this cartoon Feynman diagram, right? Again, indirect direction, direct direction colliders. So what have I done? I've actually done solar capture. So there's a dark matter particle scattering with the solar electron, and the dark matter particles get captured. So I looked at the picture in this way, bottom up. I can look at the picture from left to right. Now there are lots of dark matter particles getting captured. Remember that then asteroid mass of dark matter particles captured inside the sun. What happens if they annihilate? Right? There are lots of particles captured near the sun, solar core. What happens if they annihilate? They can annihilate to produce Stern-Malt particles, and you basically look at the plot from this figure from left to right. Right? So the question is there a measurable effect of these captured dark matter particles? The answer is yes. So can we detect the signature of the dark matter inside the sun? So what can come out from the sun? Well, these dark matter particles basically gets captured. These dark matter particles settle down at the core of the sun, all right? And the only thing that has a remote chance to even come out from the core of the sun are neutrinos, all right? So this is basically the cartoon picture. The dark matter particles are inside the sun. They produce various standard particles, and the neutrinos will come out. But even that is not easy for the neutrinos. The solar core is extremely dense. So the neutrinos are the only particle which can travel from the center of the sun, but the solar core density is 150 grams per cubic centimeter. It's more than 100 times than the water density. The solar core radius is this number. This is basically 20% of the solar radius. That's the size of the solar core. That's where the dark matter particles are. That's where the interactions are happening. And neutrinos, suppose you take a 100 GeV neutrino. What is the mean free path inside the solar core? Is roughly this number, 1.6 times 10 power 10 centimeter square. Solar radius is this, right? So if you take a 100 GeV neutrino, take it to the solar center, just leave it, it will scatter once within the solar core. That's what this number means. What about antineutrinos? Again, 100 GeV antineutrinos, it has the same number. If you take an antineutrino, it will scatter once within the solar core. The solar core is extremely dense. However, neutrinos and antineutrinos are the only particles that can inform us about the dark matter annihilation inside the sun. Okay, so where will the neutrinos come from? So this is where again particle physics comes in. Particle physics will tell you that if you have any process producing any standard particles, you will produce neutrinos. So let's do this process. Two dark matter particles annihilating to electrons and positrons, right? So figure from here to here, left to right. Chi goes to E plus E minus. You can show, not you can show, this is inevitable that there will be a Z boson being emitted from the final state electrons or the positrons, whatever. This is basically like bremsstrahlung. This is how bremsstrahlung happens, except this is electroweak bremsstrahlung. Bremsstrahlung is photon bremsstrahlung, gamma, right? Here we are using the electroweak bosons, Z. Once Z is produced, it will produce neutrinos. That's it. That's where the neutron comes in. You can do many elaborate particle physics models. No matter what you do, you are guaranteed to produce neutrinos if the dark matter particles are heavy enough. And I'll show you what does heavy mean. Right? So due to electroweak corrections, so this is electroweak corrections or electroweak bremsstrahlung, whatever you can talk about, you can think of it. A large number of neutrinos and antineutrinos of all flavors will be produced from every standard final state. No matter what dark matter goes into, neutrinos will be produced. So typically, electroweak corrections are relevant for dark matter masses of greater than 500 GeV. Right? So there's some standard particle physics you can do, and this is the number comes out. Typically, if the dark matter masses are greater than 500 GeV, electroweak corrections are super important, extremely important. And there is a large amount of literature dedicated to understand these electroweak corrections for various dark matter annihilation channels. All right, so these are two of the main papers here. All right, good. So how does the neutron spectrum look? So what is plotted on the x-axis is the neutron energy. What is plotted on the y-axis is the d and d, the number of neutrinos per unit energy interval. Here I am assuming the dark matter mass is 1 TeV, and what is happening is dark matter produces E plus E minus, and finally that produces neutrinos. All right, again a guaranteed process. This step is guaranteed. From here to here is guaranteed. If you include how the propagation looks, basically the figure is this line. All right. So once the neutrinos are produced inside the sun, they have this solid line. That's what the spectrum looks like, right? But then these neutrinos get absorbed. The final spectrum that we find is this dotted line. All right. As I said, all flavors of neutrinos and antineutrinos are produced. All right. And there is actually as you can see, important effect of the propagation inside the sun. While the neutron is propagating, it's an important effect. All right. So there is a huge change in the spectrum. All right. Note that there is a capture rate here and there is an annihilation rate, and you can show that these are in equilibrium. The annihilation rate is proportional to the capture rate up to a factor of 2. All right. This tells you that only the capture rate is important here. Okay. And this is just tells you what is the neutron antineutron flux. Some equations, don't worry about it. Depends on how far away the sun is. That's the distance to the sun, flux, d and d, and the annihilation rate. Okay, good. So how do you detect these neutrinos? This is where something which was hinted in the previous talk, neutron observations, comes in. We know extremely well how to detect high energy neutrinos. The detector to use that I'll be talking about is Ice Cube Neutron Telescope. So Ice Cube is a neutron telescope in Antarctica. It has started the field of neutrino astroparticle physics for the last 10 years. right? It has opened up a new way to probe relativistic astrophysics. What you do is you go to Antarctica, you dig some holes, basically pour hot water in Antarctic ice, the water melts, you put your detectors, and then the water freezes. That's how you build a detector. And there are 86 strings. It has been completed in 2011. It's a gigaton detector. What does it mean? Its effective volume is cubic kilometer, kilometer. Right? It is taking data from 2011. As I said, it has been a fantastic detector. It has made epoch-changing discoveries, and still going on. The minimum energy that IceCube can detect is 100 GeV. Right? It can go. In fact, it has a detector inside called deep core, which can go to even lower energies, 10 GeV. The way you detect neutrinos is neutrinos will come in, produce the corresponding charged particles, right? Say muons. The muons will go through the ice, and you see the chain curve light, and from that you can detect neutrinos. All right. So let's talk about our results. So IceCube has directional capabilities. I remember in the earlier talk there was mentioned that IceCube has detected neutrinos from a flaring gamma ray AGN, TXS Texas source, TXS 0506 plus 056. So IceCube has a pointing capability. So it is a 4-pi detector. That means it looks at all parts of the sky, but it also has a pointing capability. The cartoon is as follows. This is the sun. It's producing some neutrinos. Neutrinos will come in, produce a muon, and you can detect the muon. And from this, you can reconstruct the direction of the sun. All right. So the idea that we have is as follows. If you have the solar opening angle, that means this angle, if you measure the solar opening, what is the angle of the final state muons? So here I am detecting muons, all right, with the sun. This is it. This is solar opening angle, cosine of the solar opening angle, and the number of events in IceCube on the y-axis. There is backgrounds. This is the IceCube. This is the atmospheric neutrino. This background. This is the data points. This is the error bars. And if you assume that dark matter particle has a mass of 10 power 3 GeV and cross section is 10 power minus 37 centimeter square, and dark matter particles annihilate to tau plus tau minus, this is the histogram. All right. So you see a clear excess. If dark matter particles existed with these properties, we would have seen it. This is, by the way, this is real data of IceCube. We would have clearly seen it just by eye. You don't have to do any special sophisticated things. All right. We have not seen it, obviously, otherwise you would have known, right? So the event number due to new physics, this is the new physics, dark matter producing tau plus tau minus, exceeds the observed data. What is the observed data? This, which agrees with the atmospheric neutrino background. So thus, we cannot claim that we have discovered dark matter, but we claim that there is a constraint on new physics. All right. So how do the numbers look like? So what is plotted on the x-axis is dark matter particle mass in GeV. Y-axis is dark matter electron scattering cross section in centimeters squared. This plot is dark matter goes to tau plus tau minus. Remember I told you, you can take the laboratory limits and you can go 1 over m chi. Suppose you go to very heavy masses. This is the limit, xenon 1 ton. Anything shaded is ruled out. All right. Our limits are this, and this. Anything above is ruled out. So you can see we probe regions of parameter space which are orders and orders of magnitude larger than the laboratory limits, and these are the strongest constraints in the world. Yeah, this is something that we are still working on, but the result is final. So using the results of IceCube, we derive the most stringent constraint on dark matter electron scattering cross section, the most stringent constraint in the world. Right? These are orders of magnitude stronger than xenon 1 ton limits. Right? Xenon 1 ton only covers this patch. We cover everything here. Right? There is an older work from Super K by Joachim Kopp et al. This is this line. And note that IceCube will run. IceCube will observe things. And there are IceCube upgrades, IceCube Gen 2, which is funded. There is CAME3Net, another neutron telescope at the Mediterranean Sea, which is funded, which is being built. And there are other neutron telescopes. If you build a neutron telescope, it will almost certainly look at the sun. It doesn't have to look at it. It's a 4-pi telescope. It will always look at the sun. So there is a tremendous discovery potential. As you run these detectors longer, these constraints will keep going down. Hopefully, you can either discover dark matter or maybe rule out parameter space, which cannot be probed by any other mechanism. This is the same plot, except I'm assuming dark matter goes to nu bar. Right? Again, you see this is the old limit of xenon 1 ton, and we probe orders of magnitude larger parameter space, which has not been probed before. Again, there are future upgrades of detectors being built, funded. These will come online within the next 10 years. IceCube will run. There is also CAME3Net, Antares. All of them will run, and there is a huge discovery potential of dark matter using this technique. Okay, so I conclude my talk. So I've tried to convince you So whenever there is a tension, one should look for an opportunity. That's an opportunity to do something really new. So I have talked about the tension, the fact that we are not discovering dark matter candidate, in the sense that what are the non-gravitational interactions of dark matter? We do not know that. So this implies we must probe all regions of the dark matter parameter space and all kinds of dark matter Stern-Wald couplings. We probe dark matter captured inside the sun via electron scattering. Then they produce neutrinos, and we probe that. For various final states, we derive the world's most stringent bound on dark matter electron scattering cross section for heavy dark matter. And as I said, there is a near future guaranteed data set. This data set will be there. There is no way stopping it. And this has the potential to either discover dark matter non-gravitational interactions technique, or maybe rule out parameter space, which cannot be ruled out by any other technique. Thank you.
Yeah, Kaushik. You want to ask?
Yes. So Ranjan, thanks for the talk.
Yes,
so
nice.
I presume that all of your constraints in the end coming with this assumption that particular channel has a 100% branching ratios.
Good, yes.
And for example, even the very initial indirect detections constraints, those all of them relaxes. I mean, as you. So how, I mean, even your final conclusions changes where you pick up this very particular, possibly favorable branching fraction?
Yes. Okay. So the question is, so here I'm assuming dark matter only goes to nu bar. What happens if it's a fraction? Then you just scale up these limits. That's it. It's just proportional to it. You can just scale up these limits. Similarly for tau plus tau minus, you just scale up these limits. So it's a proportionality constant. That's it. Yeah. And then if you have a particle physics model, you can actually tell what is this proportionality constant. I mean, we are just assuming its proportionality constant is equal to 1 for simplicity. But you can scale it up and using a model. We are sort of doing a model independent approach. We are not assuming any particle physics model. Does it? Yeah, we are assuming 100% branching ratio. Yes, that's an assumption. Yes, but the point is, no matter what you do, tau plus tau minus nu bar. I didn't show the electron limit. The electron limit is very slightly weaker. I can show you. Yeah, the electron limit is very slightly weaker than the xenon 1-ton limit. But the muon limit is actually stronger than the xenon limit. So no matter what leptonic channel you use, we almost always get the best limits in the world. Thanks.
Yeah, sir.
Sorry? Yes. That is just order 1 change. So this is assuming, when I say nu bar, it assumes 1/3 nu v, 1/3 nu mu, 1/3 nu tau plus antiparticles. Yeah, this is just an order 1 change. You can do this thing.
Sir, thank you for the excellent talk. So I have just a small question that you have previously, like in particle dark matter, given a bound over that. I mean, what should? So is it for only WIMP or like some MSSM, or if I take a effective field theory, that is also true? Like it is from unitary bound from S matrix or some quantum field theory?
Yes. The unitary bound that I shown comes from the S matrix argument from quantum field theory. So that is always applicable if the dark matter is a point particle and if the dark matter is produced thermally. That bound is always applicable.
Okay, so it doesn't matter if it comes from MSSM or
nothing.
Like
yes, it just comes from basic quantum field theory,
okay.
S matrix.
Sure, thank you, sir.
Yeah.
Hello.
Hi,
sir. Here, at the back.
Okay, yeah, whatever.
Sir.
Okay, yes.
I have a doubt in the indirect dark matter detection slides that you said.
Yes.
So, for indirect detection to happen, dark matter particles should interact with each other and form the standard model particles. Now, from what I know, when dark matter particles freeze out, the order of magnitude of that temperature to the mass of the dark matter candidate is almost equal. So,
1/20th, roughly.
Yeah. So my doubt is, given the present temperature of the universe, how can we be so sure that heavier mass dark matter particles can be detected using indirect detection techniques?
So let me rephrase the question. The question is, initially the universe is very dense, all right? That means huge amount of dark matter density, dark matter can collide. Now the universe is not dense, that's what the temperature means. The universe is expanded, the universe is very less density. How can dark matter particles even collide, right? I'm saying initially it's colliding, then the density has increased, it has stopped colliding, and then suddenly how come I say it's colliding? That is, it collides only in the dense parts of the galaxy, in the universe. So what does that mean? You see the density in this room of the dark matter density in this room is 5 orders of magnitude larger than the dark matter density in the universe. If you take the dark matter density in the universe as a whole, it's 5 orders of magnitude less than the dark matter density in this room. So in the universe as a whole, the dark matter is not interacting, dark matter is not colliding, but there are small pockets where dark matter is colliding. So this is sort of like this plot. You see this here, yellow or orange is basically the density is higher. So this is where dark matter collisions is happening. This is not where dark matter collisions is happening. This is where dark matter collisions is happening. This is the whole space, whole universe. These bright spots are where these are regions where dark matter collision is not happening. Dark matter collisions again start simply because we are in a region of the universe which is much denser than the universe as a whole. That's why dark matter collisions again happen. The sun is also basically like that. Sun has lots of dark matter packed inside a small region. The density is very high. That's why the dark matter annihilation again starts.
Yeah, I'm sorry, we are running very short of time. So please catch the speaker during the break and then ask all the questions.
I'll be here for all days.
So let us thank Ranjan for the time being.